Hello! Today it is going to be Sound and Syncs Part 2. Now, it has been a good month or so since the previous video, and in that time I've learned quite a lot more about the equipment, and I've also received a number of interesting emails. So today we have a number of new things to talk about and a few new tests to perform on the equipment, and also on your patience. Now I'm actually going to start off with one of the most unexpected emails that I received, and in this previous video I speculated whether or not Philips ever developed a NICAM reframer product. Well, since then we actually heard from Sten from the original team at Philips. Yeah, they did have one. In fact, he actually developed it along with a number of modules from the equipment that we've been using throughout these videos. It was originally developed for the Danish TV2 who used it throughout the country, and this is quite an interesting thing to hear because it tells us that these more sort of elaborate NICAM installations, which I previously have said were mostly confined to the UK, actually these did exist elsewhere. Now this reframer, this will also have been a catalogue product, but I have to stress that such a catalogue is not something that I've personally ever seen. In the previous video, I talked a bit about a mysterious, ill-fated NICAM-676 or NICAM-3 based SiS solution developed by TVT, which has long been rumoured to have existed and is briefly mentioned in at least one BBC publication. Well, some quite specific details about that equipment has since turned up. Here is an actual brochure for it. It was a fully developed solution which looks rather similar to the kit that we have here, but internally it is quite different. This was an unfortunate misstep for TVT because this system most likely had no customers. It cost them valuable time and opened the door to the competition, who ended up dominating a market that they should have been leading. The remaining question is how exactly it happened. In search of answers, I reached out to John Robinson, the designer of the BBC's NICAM-3 ASIC. This chip has had plenty of press over the years, so we won't get heavily into it today. It turns out it was originally designed for the NICAM-676 based SiS equipment. If you're going to the trouble of designing a chip for something, you're generally pretty certain that you're going to use it. Working closely with BBC Designs, TVT would have been reassured that the kit that they were producing would be purchased by the BBC at the very least. But over at BBC Research, something different was quietly brewing: NICAM-728. With a higher bit rate, which it mostly uses for additional parity bits, in the end it would be selected for television, and TVT, one of the BBC's oldest and most loyal suppliers, basically got pushed under a bus. At this point, it may have made more sense for the BBC to have booked a ticket to Denmark, but that would have been pretty ouch. Unfortunately, John's NICAM ASIC wasn't able to be used for 728 because it can't handle the differing parity scheme, but at least it found an application in FM radio, and as of a few years ago it was still in use in many locations throughout the UK. Next up, a revisit of the demo of the TVT reframer from the previous video. Having only one coder, it ended up rather mediocre, and I knew that I could have done better, I just didn't have sufficient information at the time. Since that video, some of the documentation for the TVT system has turned up. We now have a detailed description of how it works, connector pinouts, and block diagrams. And we also have the full service manual for the decoder, but unfortunately not the coder. This all came from Paul Reed, who has done quite a bit of work on the MCR21 project and can be seen in a few videos on their channel. The link to the manuals is in the description. To see the TVT reframer in action, we need to get a bit more familiar with those auxiliary connectors on the rear, which we did briefly cover in the previous video. Today we need to look at the input, however, first of all, some new things that I learned about how the output was used. In the making of this video, I stopped off at one of Britain's most niche museums, the BECG. For anybody with an interest in this topic, this place is as good as it gets. It's staffed by industry veterans who will tell you anything that you want to know. There's loads of equipment on display, and quite a lot of it is actually working. A single day just didn't do it justice. Of particular interest today is some of the insides of the Crystal Palace analog transmitter, including a massive Harris clustrode transmitter which was saved from the scrap heap. Even the input equipment was there, but unfortunately quite a bit of it had already been pilfered by the BBC before they received it. That's where one of the SiS decoders went. Here is the connector which mated with the auxiliary output, and we can see that it has a pair of coaxes coming straight out of the back of it. Likely no conversion electronics at all, unlike my previous demos. The coaxes are NICAM data and clock connections which head off to the modulator. This Tektronix 728M is the actual modulator it was connected to, and we also have a monitoring decoder on top of it. These are both fancy 1990s items, unfortunately not what the transmitter would have originally been equipped with in the 1980s. But looking at the rear, they have the same type of input as the Philips coders that we saw previously. I wasn't able to connect the auxiliary output directly to the equipment that I have, so this kit has either been modified or has the option for a unipolar input. And this makes reports of analog connections to SiS decoders even stranger, because this just doesn't seem to be necessary. So given that I only have the one SiS coder, how am I going to make the reframer do its thing? Well, in the previous video I talked briefly about this auxiliary input connector, and I speculated that this was probably for some kind of digital input scenario where you can feed a NICAM bitstream into the SiS coder, effectively not using the NICAM coder contained within here. And there are some scenarios where I think this would be used in the real world. I had a look at the street view of the old television center, and we can see these coders here. These appear to be the outgoing coders for BBC 1 and 2. And we can see that they don't appear to have analog audio inputs fitted. So this would suggest that they are being fed with a digital input from somewhere else. And having a bit more of a look around, I also found a decoder here, and this one doesn't appear to have the analog audio output connected. So this one looks like it's being used to extract the NICAM bitstream from maybe an incoming feed. And so yeah, I do think this was probably used in the real world, but the problem has always been I don't really know how to actually use this connection here. I don't know what the pinout is, I don't know how to actually activate it. But of course we do have the full documentation. Well, not the full documentation, but we certainly have enough documentation to know how to use it now. So we have the description of the auxiliary input here and all the information we need to do this. And we can see here that it is an RS422 type of interface, balanced 5-volt signals. So this is a unipolar signaling, so we don't see any negative voltages. And we also have all the pinout here, and data and clock pairs, and also this C0 input here. This is a synchronization signal which is optional, and it's used for synchronizing all of the electronics in the coder. Quite interesting, but we're not going to be using that today. And certainly this is quite an unusual type of interface. I've never seen any other equipment with an input or output like this. So the question is, how are we going to be converting from this type of interface to our Philips style interface? When I say Philips, certainly a lot of other manufacturers used it too, but they do seem to have been the first. And this is the solution here, and this is hot off the press. This PCB on here actually just came in yesterday afternoon. And what we have here is two BNC connections, so data and clock, and the output here is on this 15-pin D-sub, as we would expect. So let's grab the schematic for this and have a look what's going on that PCB. So we come in here as a bipolar 75 ohm type of interface, and that is terminated here on these 75 ohm resistors. From there we head into this ultra high speed RS232 receiver. And bear in mind that 728K is pretty damn blistering for RS232, so we do need a pretty speedy part there. And the output of this is TTL. That then heads into this RS422 line driver, and then we exit from here as our differential RS422 signals into the SiS coder. So pretty straightforward there. And could I have done it with fewer components? Yeah, probably, but this is a pretty nice receive interface, which I think should work pretty well. So let's just quickly talk about the test setup here. Now on the top I've got the IBA style coder. This is the one from RE Technology, and I'm just using this as a NICAM coder at the moment. So audio test signal coming into the analog inputs, and NICAM digital bitstream coming out of the rear. Normally you would use the SiS output, but because of course we don't have the decoder for this system, these are basically useless at the time being. And the speakers here are actually connected through a converter which comes from the stereo output on the rear of the SiS decoder, which I haven't really used much previously. And another thing just to point out here is that when I first turned on this setup for testing, this coder actually went pop, and I've got a little section at the very end of this video where I did a small repair on this if you want to watch that. So what the heck are we doing here? Well, now that I have the ability to supply my own NICAM bitstream into the coder, I can of course switch this input and introduce an error into the NICAM bitstream, which will force the reframer in the decoder to act. So basically this allows me to combine the two demos that I did, the very first one with the Philips equipment and the second one with the TVT equipment. But there's actually another couple of things that I want to demonstrate since we've got this set up here, and the first of all is a rather interesting scenario where the IBA and the BBC source from each other. Because of course they have incompatible SiS systems, there is a slight problem here. And what they basically did is had a coder and a decoder back to back, and they take the NICAM output from one and feed it into the input of the other. And that basically allows them to translate between the two systems with no loss of audio quality whatsoever. But there is actually one other scenario that I want to demonstrate here, and this is just something that I came across by accident. Let's turn up the volume on this setup here. I'm just going to unplug the inputs now. So what you heard there was an error tone, and this is generated by the SiS coder when it is set up for a digital input and it has lost that digital input. Kind of an interesting thing. And imagine if the BBC had have transmitted that racket to the public. That's the kind of thing that gets British viewers writing letters. Anyway, that's enough about this setup here. Let's reassemble the original test setup. So let's just have a quick overview of all of the connections here. It's pretty similar to what we had before, but just with some extra stuff in here. So as with before, we have the two studios. This is the Alpha Studio that you can see in here in view, which has two main outputs, so the NICAM bitstream and the composite video, that's this one here. But notice this time we have a second connection on the NICAM coder. This is the NICAM clock, which we don't normally use, but as I say, the TVT coder does require this, so we're going to be running a clock from each into the matrix switcher. And going up here, of course, we have now 6 inputs to the matrix switcher, so that's 2 composite videos and 2 NICAM data and 2 NICAM clock connections. And the outputs here are composite video, NICAM data, NICAM clock. And those, of course, are heading into the SiS coder here, so that's the NICAM data and clock, headed into this auxiliary input that we just talked about, and the composite video input right there. And there's the composite video output from the SiS coder, or the SiS output, I guess, and that heads into the SiS decoder, and from there we have 2 outputs. So there's our recovered composite video output, and there's the NICAM digital bitstream, and these two are headed down to our transmitter. So as I say, it's a fairly similar setup to what we had before. I've kind of built it this way mostly for thermal reasons actually. These two run really hot, they do need to be at the top where the air can come out. So we're just going to have a quick look at the back of the transmitter side of things now, and I realized that contrary to what I said in the previous video, I've never shown the back of all of this before. So we've got 3 main connections coming from our SiS decoder here. The yellow one is headed into the NICAM modulator, and that of course is our NICAM digital bitstream, terminated 75 ohms there. This one here is the analog mono audio output from the SiS decoder, which is headed into the vision modulator, and I realized that in the previous clip I had forgotten to connect this one. Whoops, so we'll hook that one up now. And this one here is the recovered composite video signal, and that's coming from the SiS decoder also. And the outputs of these 2 modulators here are IF signals, so this is the NICAM IF, and this one here is the Vision IF. Now the Vision IF heads through this cable here into the channel converter, and it just goes straight through. The NICAM IF goes into this input here, and this is directionally coupled onto the Vision IF. So that means that the NICAM carrier will only exit through the output of the directional coupler, and it will not go back out of this connection here into the modulator, because of course we don't want that. And the output of the channel converter here is on UHF channel 21, and that's headed over to our receiver. Okay, so we're up and running now, and we're going to have to be rather hasty because I've got about 10 minutes before that whole setup overheats, and I can already smell it getting a bit toasty. Now pay particular attention to the TV here. Remember last time we had that NICAM indicator flashing on the screen when I switched between studios, and you could also see the NICAM indicator flashing off and on the VCR. The audio output on my TV is completely screwed, and if I was a proper vintage TV channel, I'd probably do a video about fixing that, but I'm not. So I've plugged in my computer speakers to the VCR. We'll just turn up the volume now and listen to that test tone. And we'll do some switching. Oh yeah, that's so much better. Just a small interruption there, but that's completely to be expected. Switch off that noise. Well, there you have it. TVT reframer doing its thing. Well, I'd be tempted to say you saw it here first, but anybody living in the UK, of course, spent a good couple of decades seeing this. But anyway, that's basically the deal here. And the little small interruption that we get, that's actually to be expected, and it does actually say in the manual for the decoder precisely how long that interruption is, because the reframer does take a little bit of time to realize that there's been an error in the bitstream and to recover from it. But certainly pretty good, and it's a lot better than what we saw before. And in reality, that interruption of audio is just not going to be a problem, because that's going to be a switch from an OB van or a regional studio to a central studio. There wouldn't be continuous audio in that scenario anyway, so nobody would notice anything. Anyway, I hope you enjoyed this demonstration. Let's get on with the teardown. So let's have a quick look at the physical construction of these units, because I think they're kind of interesting. This, of course, is our TVT decoder, and basically the construction of it is fairly simple. It looks like it's been put together with, I would say, more or less off-the-shelf metalwork, maybe with a little bit of customization. The serviceability of this unit here is really just fantastic. All you have to do to get in is rock up with a pair of opposable thumbs, and basically you're in, no tools at all. And once you open this front cover here, you've got this little diagram here with basically descriptions of what all of the LEDs are and what the modules are, which is pretty cool. I mean, I guess it could be on the front panel, but yeah, it's nice and helpful, certainly. And in terms of getting the modules out, all you've got to do is just grab one of these levers and eject them like that. So yeah, that's you couldn't really ask for much better than that in terms of serviceability. I really like that. But yeah, I don't like these plastic levers. None of mine are broken, but I'm sure they are easy to accidentally break if you're not careful with them. So we just flipped it over here, and one thing to note is that I didn't remove any covers here. It's an open frame design. Now the advantage of this is that you can stack up a whole column of these things, and the airflow through them is pretty much excellent, but the disadvantage, of course, is that as a standalone unit, they're quite flimsy. The chassis can skew very easily if you're not careful with them, and certainly when you're using them just standalone, there's quite a lot of hazards involved, which I'll run through. So there's a mention of live mains terminals under here. I don't know how severe that risk is, but yeah, certainly I'd be quite careful about that. And also, if we look at the backplane here, we've got these press-fit connectors on here which have these really long pins, and those are actually all of the power rails here, and the 5 and 20 volt rails are basically right next to each other, and there's no overvoltage protection in this unit at all, and you certainly don't want to be accidentally dropping one of these guys in here while it's on. And another thing to note is this PCB here is one that I've added, and this just nicks a bit of power off the backplane, and that's for feeding these little connectors which I use for powering the interface converters. Now this unit, of course, isn't an open frame construction, and that has the advantage that it's a lot more robust, but the disadvantage that you can't stack them all on top of each other in a rack. There is a minimum spacing between each unit, which is specified in the manual. Connections on the rear are really nice. Everything is all sort of industry standard here. So the NICAM digital connections are 75 ohm bipolar, which is used by basically every manufacturer other than TVT. And our RS-232 connections, standard pinouts, and standard XLR connections here. So this is a really nice, easy unit to hook up to. And these B&C connectors are true 75 ohm B&C connectors. Not really a lot of point in doing that in this application, but they did it anyway. Very nice. So these are the audio input modules from all three systems. They all do exactly the same thing. They take a balanced analog audio input and they output a PCM digital bitstream. And these two here are from the RE Technology Coder. These two are from the TVT Coder, and this is from the Philips Coder. One thing to note here is that we have Philips part numbers on the TVT modules, and that's because these were designed when Pi TVT was owned by Philips. So we'll start off with the RE technology modules. Now, one thing to note about this is that we have a module per channel, which is pretty luxurious, and they would have done it this way because some of their products can end up with an odd number of channels and they're just using the same module for everything. Now, the design of it is pretty dense, so they've packed a lot of stuff into a small space here. We've got an Analog Devices 16-bit ADC, very nice part, and built-in front end, I believe. And this here is all of our pre-emphasis and pre-amplification and what have you. And that's the anti-aliasing filter there, so that appears to be an off-the-shelf part. But yeah, the components used, all very nice quality components here. These orange ones are solid aluminium electrolytics, very nice, and film capacitors everywhere else. So nothing that's going to fail there. Now for our TVT input, it's a much sparser design split across two different modules. These are balanced input transformers, so that's quite a deluxe feature there, and we don't have that on either of the other two systems. Reefer low-pass filters here. These are for the anti-aliasing, off-the-shelf parts by the looks of it. And we've got various amplification here as well. Now, one little banana peel for newbies here is this monitoring jack here. You'd think this would be a 1/4-inch jack, but that doesn't actually fit in there. What actually that connector is a B gauge connector like this, which I had to make up a special adapter to use that. These were used quite commonly in telephone exchanges. I don't know why they've used that, but anyway, that's what they use if you want to plug your headphones into it. Now coming over to here, this is where the actual digitization happens, and we've got just a few little sprinkling of logic chips on here, and we've also got this Burr Brown ADC here, 16-bit, very nice part. That's just a very BBC design. Certainly any digitization I've seen from the BBC, it's always a Burr Brown. And analog front end, well, looks like they didn't really want to design that, so they just bought a module here. I'm sure the performance of this is very nice. It certainly sounds very good, but yeah, I wouldn't want to have to try to find a replacement for that. So this one here is our Philips audio input, and it's rather different to the other two. Pretty much built entirely out of Philips components, or Signetics components, which was Philips. And anywhere a Philips component wasn't available, they have just gone and built that function from scratch out of Philips components. And this anti-aliasing filter is probably a fantastic example here. Anti-aliasing filters for audio are really, really difficult design, and they clearly didn't have one in their catalogue at the time, so they just designed one from scratch, and the performance of this is very nice. I've actually swept that with test equipment. Anyway, let's whip that one off and have a look what's underneath. So under here we have, once again, a lot of stuff that has been designed from scratch. So that's an analog front end down here, and clearly at the time they didn't have an ADC with a front end, so they just designed one from scratch using Philips components, of course. And this here is a TDA1534 14-bit ADC, and I think at the time they wouldn't have had a 16-bit ADC, unlike the others, which these are all both 16-bit. Philips was a 14-bit company at the time this was designed, so that's all they would have had. Socket for a second one there, and presumably this thing has an option for a second ADC. So rather than switching the left and right between this one chip here, you can basically split it in half, I guess. I don't know. I've never seen the schematic for this, so I don't actually know entirely what that socket is for. Next up we have some NICAM coders to look at, and we have 3 different implementations here, all do the same thing, but once again all completely different. This one here is from RE Technology, that's the TVT version, and that one is the Philips. And we're going to start off with the RE Technology coder, and it's actually a triple G's design here. It's split into 3 different PCBs. I had a bit of a job trying to get that apart. The top PCB isn't really all that relevant, so we just got an audio monitoring circuit here for some headphone jack, and we've also got the clock circuit here. So this is a TCXO, which clocks the NICAM coder. That's quite fancy. I've not seen that on any other designs. But the actual design of this is really interesting because they got it done with such simple componentry. If you look closely, there's basically nothing other than discrete logic chips and a few proms on here. So yeah, I'm really quite impressed that they managed to do that without having to reach for microprocessors or DSPs or anything like that. And next up we have the TVT design, and it's my understanding this was the last of the three to be designed, and being last was an advantage because they were able to use this TMS 320 series DSP, which came out at the end of 1987. I think when certainly Philips were looking at this, that wasn't available, and there's not really a lot else to say about it other than that, yeah, it's all happening inside that DSP. And finally here, the Philips. This was the first to be designed. It was completed in late 1987, and yeah, it's a pretty crazy design here. So basically, the NICAM comes into this dual-port SRAM. It's then picked out by this massive 68K processor, which does the encoding and feeds it back into this FIFO, which then basically gets reserialized again and goes out the back. It's really just quite a crazy design there. And one thing I heard about this from Sten is that when they were designing this, they actually didn't know how NICAM-728 even worked, and they were really just guessing. And looking at the spec, it doesn't actually appear to have been published until a good 6 months or so after they actually completed this. So that's quite an interesting thing about it, and it just really shows how early Philips were looking at this. Whereas I think these other two, these were later, maybe 88, 89, these were probably completed, these designs here. This one may have been even later. It's quite hard to tell, unfortunately, without having the inside story. So from this point onwards, the design of these systems starts to diverge quite considerably, and the Philips system drops out because, of course, it's not SiS, and there's nothing else to look at from that. These modules are from the RE Technology kit, of course, and this is the SiS buffer, and this is the async data processor. Now, it's my understanding that these two roughly do the same thing. So they take the NICAM-728 bitstream in, and they prepare it as basically a set of data bursts ready for insertion into the video signal. So it's kind of like a synchronous to asynchronous conversion process. Although I think probably some of this in this system is being done elsewhere, because this thing looks a lot more complicated. We've got these field programmable logic sequences on here, whereas this looks a bit too dumb to be doing the job. As I say, it is quite hard to make exact comparisons. And I don't think there's a lot of point in going into detail about how they work, and we don't even know how this one works anyway, because we don't actually have any documentation for it at the moment. But anyway, there's a brief description there. So we've got another couple of modules to look at here. This is the sync separator and regenerator from the TVT Coder, and this is the SiS inserter from the RE Technology Coder. This one here does all of the sync processing for the unit, and unfortunately I can't tell you how it works because we don't have the documentation for that particular module. However, we do have the full documentation for this one. Unfortunately, there is just so much of it, and we can't even go into detail about all of this anyway, because we would be here forever. This particular one is actually 4 PCBs in one module, so yeah, if you want to work on that one, it's a bit tricky. You'd have to basically dismantle it and try and maybe extend each module individually. To some extent, but this one actually sandwiches on top of that one, so it makes that one a bit tricky. The other thing I found interesting is it has quite a lot of rework on it, which is unexpected, because my understanding is this is probably one of the later units to be manufactured. Oh, right, so back again after spending about 10 minutes trying to put that SiS inserter back together again. Next up we have the Coder video processor from the TVT Coder, and this is the SiS encoder from the RE Technology Coder. These, once again, are not directly comparable, but I've put them both together because they both do the job of inserting the SiS data burst, so the digital to analog conversion happens on these PCBs. And certainly a very different approach. The TVT one is very analog and very old school, whereas the RE Technology one just uses this TRW ultra high-speed video DAC here, a very expensive part, and certainly to my mind that's a pretty overkill way of doing it, but anyway, that's what they did, and certainly this was put together very quickly, whereas this is probably, I would guess, actually fairly similar to the original mono system that would have been developed in the 1960s, or certainly a derivative of that design. So here is a particularly interesting module from the TVT Coder. It is the CPU board, or the monitor as it is described there. Notice that we have a Zilog Z80 there. Now, it didn't even occur to me originally, but this actually turns out to be a BBC Micro. That's the BBC Basic PROM there, and that's the program that runs on the module. It's in plain text in the BBC Basic language, of course. And this is a rather unusual feature in this product in that it actually comes with its own source code. And I think it was done this way because this derives from an internal BBC prototype. So yeah, it looks like TVT basically just took it as is and maybe made a few tweaks to it. Now at this point we have moved to the SiS decoder, and of course we only have the TVT decoder to look at. Now I've picked out 3 modules, and these are basically the ones which process the SiS data burst. The video signal comes into the decoder video processor. This basically has all of the input circuitry, and the recovered composite video output also exits from this module. However, the actual recovering of sync and stuff is done in conjunction with this module here, which is the sync separator and regenerator. And this one does all the really clever stuff of actually finding the SiS data burst and synchronizing with it, and oh my gosh, there is a lot going on there. Unfortunately, we just can't get into it once again. Now, the output of this module is, of course, the SiS data burst, and that heads into this quaternary ADC. And once again, just look how complicated this is. Really, really complicated, and all sorts of stuff going on here. Basically, the input of this will, of course, be the analog SiS data burst, and the output will be basically bursts of NICAM data, which are processed further a bit later on. So this is the next 3 modules in the process. This is the data recovery board, and this takes the raw output from the quaternary ADC, which is still fairly unprocessed. So all of the various intricacies of how it actually gets encoded into the data bursts are still present. And the job of this board is really to just do a bit of further processing and actually really produce the raw NICAM data that we ultimately want. And that, of course, is fed into the bitstream regenerator. And this board's main job is to basically convert it from this asynchronous burst type data into the synchronous NICAM bitstream that the rest of the unit requires. After that, we have the reframer, the infamous reframer, which once again is pretty complicated, but notice that we don't really have any sort of CPUs or DSPs on here. It's all fairly basic componentry here. The main guts of it is this FPLS here. This is a field programmable logic sequencer, which seems to be doing all of the clever stuff, and certainly this is actually one of the most exotic programmable devices that I have ever seen in my life. Very, very difficult to find a programmer to work with this, and I do want to get the code out of this, but I'm going to need some help from somebody else to do that. Anyway, let's put these away and get to the next lot out. So we're now back in the more pedestrian world of NICAM decoders, and this is the one from the TVT SiS decoder. This is actually a Philips NICAM decoder, and this comes from one of their early monitoring decoders, the 5688. And once again, not SiS equipment, but these do both do the same thing, so I think they're worth looking at. Now on the TVT unit here, we have this Texas Instruments CF70123, which was commonly used in consumer devices. The first generation of NICAM receivers pretty well all used that chip because that's all that was available at the time. Philips didn't get into the NICAM decoder chip market until 1990. That was the SAA7280. But if we have a look on here, we have a Philips NICAM decoder which appears to have been made in 1988, so that's actually a bit older, SAA7272. This is a mystery chip. I've never seen any documentation for it. It doesn't appear in any Philips integrated circuit catalogs either, and it's accompanied by a couple of other mystery chips here. I asked Sten what the deal with this was, and unfortunately he couldn't remember, but yeah, very interesting there. This is probably some sort of prototype solution. Both of these units also have digital filters, the SAA7220. This unit here has this extra TDA1542, which seems to be just basically a bunch of amplifiers in a chip, and it does actually have a monitoring decoder on it. So this itty bitty little TDA1543 DAC is used for just an audio monitoring output. So we have a couple of audio output boards here. This is from the TVT decoder and this is from the Philips decoder. And the DAC of choice seems to be TDA1541A. We have it on both of these boards. And this here is a picture of the decoder from the RE Technology solution. This was sent to me by Graham Sordy, also TDA1541A, and fortunately that's all that he has of it. And yeah, this for NICAM equipment, this is probably a bit overkill, and you wouldn't find this in any consumer equipment because it's a bit pricey. But for this industrial equipment, actually it's a pretty affordable chip. And we can see the digital filter present on here. For the Philips, it's back on the decoder module. Now both of them have balanced outputs, so we've got these Londell transformers here and some unknown type of probably toroidal transformer there by the looks of it. I love the big holes that they've cut out to mount those in. Monitoring output on this one, and once again that's one of those funny B gauge jacks. And noticeably on the Philips we have an LC low pass filter, which we don't appear to have on here. There might be some kind of low pass filter on there, but it must just be using capacitors perhaps. Unfortunately we don't have the circuit diagram for this one, despite having the service manual for the decoder. Apparently that one was missing. Last but not least, the power supply board from the TVT coder and decoder. It's the same for both. Certainly quite a rudimentary item here. This is basically connected to the outputs of the massive toroidal transformer on the back of it. It's completely linear and pretty damn inefficient as well. So this humongous regulator on the back of here, I think this is like a 5 amp or maybe even 8 amp 5 volt regulator, fixed voltage. You've got about 12 volts coming into this and 5 volts coming out of it, so yeah, that's burning off a lot of power, considering that there's about 5 amps being pulled out of that. And you've probably seen this sticker on throughout the video that says hot. I can say from personal experience, yeah, it's damn hot. You don't want to be touching that while it's on. Now this particular one has gotten rather toasty over here as well. This is the 5 volts fuse, and looks like maybe they had a bad connection at some point, and that's gotten very hot indeed, and scorched the heck out of the PCB. And someone's done a bit of repair work on that. I did a bit more repair work on it to try and make it a bit more robust. Now the other thing is I've actually added a crowbar circuit on here because there's no over voltage protection on this. So if you've got a short between the 20 and 5 volt rails, the whole unit would go up in smoke, and I'd rather that didn't happen. So if you short them now, it will blow the fuse for whichever rail has been shorted to the 5 volt. And we've just had a little unexpected incident here, and I was just powering on the setup off camera just to make sure everything was okay, and something went bang. Now you'll notice that at the top of the stack I had the RE Technology SiS Coder, and I was going to use that as a source of a NICAM bit stream just for, I thought it'd be quite an interesting demo. And the bang seems to have come from that piece of equipment, from the power supply here. And there's a familiar stink in the air. It's like, almost smells like a reefer capacitor. This is a really unexpected thing to find on this channel. I mean, these things are really common in consumer electronics, but these sort of unreliable parts, you don't really find them in this type of industry equipment. And looking in here, I can see there is a capacitor here that says reefer on it, but this doesn't look like the exploding variety. But the smell definitely seems to be coming out of this power supply. So, oh wow, I'm going to take this apart and see what's going on here, because I think we need to find out what's going on here before we continue with this test. So I've got the power supply open and I can't see any obvious signs of damage in here, but there is this pungent smell in the air, so something has definitely gone wrong here. And now another thing I've noticed is that this power switch here appears to have been an addition. Very interesting, because I've never seen any other pictures of a unit like this with a power switch on the front, so somebody's added that on there for some reason or other. Now in terms of what to do next, I guess maybe I'll desolder these reefers and have a look underneath them and see if we can see any signs of damage. Well, I've taken them all out and inspected them. They all look absolutely fine. This one is a bit burned, but I think someone has just hit that with a soldering iron. Looks alright. Also looks alright, working a bit higher than what it says on it. Also looks okay. They say 4.7 nanofarads, but they're all reading about 6.8, which is interesting. Also looks good. Maybe something else has blown up then. So I've desoldered a few more capacitors here, and I found something. These electrolytics here appear to be leaking, and unfortunately we have got some damage to the PCB here. It looks like the solder mask has lifted off, but the traces still seem to be intact, so hopefully I can just clean that up and put some new ones in and we can continue. Now unfortunately I haven't yet found the source of the bang, and I'm beginning to suspect I'm probably looking in the wrong place. Nonetheless, I'm glad that I opened this up and had a look, because if that had been left much longer, those traces would have disintegrated completely. Okay, so I've refitted the blue film capacitors and I also refitted the reefers. There's nothing wrong with them. And while I was working on this, I noticed there was a bit of damage to the traces under the capacitors there, so I patched it up with a bit of this copper strip here. And I also noticed there was another 4 of this type of electrolytic on this side of the PCB here, and there was also a little bit of leakage, so I've taken those ones out. I checked all of the others, they seem to be fine, so I think this lot was just a bad batch, unfortunately, just quite unlucky there. Now, a couple of things to note about this power supply. The input is 48 volts. There's a toroidal transformer in the rear which steps down from 240, and that is so that these units can be run from inside a telephone exchange. In that scenario, the toroidal transformer is bypassed. And another thing to note is that these orange capacitors, you might be thinking that these are tantalums and that they could have been the source of the explosion. Definitely not. These are solid aluminium electrolytics. There's not going to be anything wrong with them. So whatever went bang is either of these capacitors or it is something else that I haven't yet seen. Okay, so we've now hopefully finished repairing this. I've got 8 new capacitors in here. I've cleaned away that disgusting smelling electrolyte, and I've also reinstated the fuse, which previously had been sacrificed to facilitate this power switch, which is a bit dodgy, so I put that back in there and rewire the power switch so it interrupts the circuit a bit later on. So I think now it's time to put the power supply back together and give it a test. Time to switch it on. Now for this test I've pulled out all of the goodies just in case something unexpected happens. And I'm just going to switch it on here and I'm like wincing right now. That looks good. So we've got 4 power good LEDs here. Do I trust just LEDs? I'm not sure I do actually, so I think what I might do is switch that off, and I'm going to take off this blank. And I think behind here we should be able to get at the connections for the power supply. Now interestingly, these units, some of them have 2 power supplies, one providing the plus and minus 15 and the plus and minus 5. This unit has 1 power supply which does everything. Don't know why that is, but that's what I've got right here. Alright, let's get probing. I'm not even sure what the pin out of this connector is. I've got the manual, but I can't even be bothered looking at it. I'm just going to poke around and see if we can find some of these voltages. There's our 5.1, that looks good. 15. Negative 15. And negative 3.5. I wonder if that's supposed to be the negative 5. If it is, that's looking kind of low. So yeah, I just had a look at the service manual, and this negative 3.5 here, that's supposed to be negative 5. Huh. I wonder what they're using negative 5 volts for, because when this equipment was built, that's a pretty unlikely voltage to be needing for anything. I'm quite curious. It may be that this actually doesn't do anything at all. I'll have to go away and research this. So I had a look in the service manual, and that negative 5 volt rail appears to be being used by a few op amps in the video circuitry, which unfortunately we can't do anything with at the moment because we don't have the decoder for this unit. And it's also possible that it has been set to that level for some specific reason that I'm presently unaware of, so I think I'm just going to leave it alone. Nonetheless, I'm still interested to know whether or not this unit sustained any damage in that power supply incident. And we can actually test some of it. So we can test the audio ADCs and the encoder by hooking up this NICAM tester to the bitstream connection on the rear. So let's switch it on and see if we get any audio out of it. Reassuringly, we do have the stereo indication on here, which looks pretty good. I think it'll be going. Let's turn up the volume. Well, that is music to my ears, so at least we know that half of it is still working, the audio inputs and the NICAM encoder. Let's get on with the demo. Well, that is all for this series, and it is a real shame to be wrapping up without seeing the RE technology system in action, but unfortunately that's just life for this sort of equipment. It's just so unlikely to avoid being scrapped. If a decoder ever shows up, I will certainly put together a future video about it. Anyway, I want to say a big thank you to everybody who sent in information, stories, scans of manuals, all that sort of stuff throughout the making of this video, because it has just been so interesting to have all this extra information, and it has added a lot to this. And as always, keep it coming. You know, I'm always interested to hear this kind of stuff. But that is it for today's video, and yeah, thank you for watching.